I can do that.
-4.
-4 indeed. Very good. So we want to find the linearization of this function at the point 1 comma -4. Okay? So the linearization would be f of a minus f, I'm sorry, plus f prime of a times x minus a, where a is 1. So let's find f of 1, which we already have. This is -4. We have to find f prime of x, which is 2x plus 2. How much will f prime of 1 be then?
4.
Very good, awesome. So now all I have to do is put everything together. So the linearization is -4 plus 4 times x minus 1. Distribute, combine like terms, and it's done. So this is 4x minus 4 is minus 8. So this is for near x equals 1. Or if you want to write a equals 1, it's the same thing. So if we want to evaluate x squared plus 2x minus 7 near x equals 1, and we can agree with some error, because it's not going to be exact, we can use this function, which is a line. So if you want to approximate that function at 0.9, you can use this and you will get a very good approximation. If you want to approximate that function at 1.01, you can use this, and it's going to be a very good approximation. Very good. Good question. Anything else? Is there anything? Yes, Vanessa?
So just that LX. Oh, sorry.
The linearization of x. Yes, L of x. Yes, that's the function that will approximate f of x near 1. Very good. Anything else? Is there anything else that you would like to go back to? Any type of problem, any problem you worked on, anything you can think of? Nothing? Remember, it's a very good practice to review or redo your test till the end of the semester. We only had one, so after this weekend, please redo both tests with solutions till you take the final exam. Because it's very easy to forget what we covered a month ago. Harvey? I'm sorry.
I think we have 3 exams, right?
The exam is on Tuesday.
Then after that we have one more.
We have 2 more.
Oh.
Yeah. So that's why I have to
Wait, we
continue.
have 2 more including the next one?
No.
Or 2 more after that one?
A total of 4 exams plus a final exam. 4 exams plus final. So we only have had 1 exam and 1 more. So we have an exam from chapter 5, an exam from chapter 4, and a final exam left. So 2 more after Tuesday. Okay then. So let's continue. Yes, please, Brayden, go ahead.
A related rates problem.
Yes?
Page 248, number 16.
16?
Yes.
16 on 248. 16. Yes, we did that in class. That was one of the problems we did in class.
Okay.
Is it okay if we do it after class today?
Yeah, that's fine.
Okay. Is there anything else that you would like to? It's in your notes when we did related rates. It's with the person that walks towards a wall, and then there's a flashlight on the ground. You remember that? Okay. Good. Anything else that you would like to go back to, or we continue with chapter 4? Okay, so let's go back to 4.1, in which we are talking about max-min. And we said last time that if a function doesn't have a critical number, it will not have a max or min. If it has a critical number, there is no guarantee that there is a max or a min either. We need to further investigate. So let's look at another example. Let's say on page 281. Let's look at 36. 36, 281, and we have a problem in which we are given age of p, function age, the independent variable p, p minus 1 divided by p squared plus 4. The requirement here is find the critical numbers of the function. I will add another requirement, but let's find the critical numbers. So let me refresh your memory. Number 2, critical numbers can come from two sources. One from f prime of x being 0, and one from f prime of x being undefined. But the function is defined. Yes, f of x is defined. Okay? So either way, I have to find the derivative. So let's find the derivative. Can anyone dictate the derivative? This is a good practice for Tuesday. Top function prime is? Very good. So then p squared plus 4 minus top function times the denominator prime. Excellent. Over p squared plus 4, everything squared. Great job. We have to completely simplify this. So then we have p squared plus 4. I distribute 2p to these two terms. Negative 2p squared plus 2p divided by p squared plus 4 squared. Let's take a moment and see if this is okay. Is this okay? Yes? Good. Now we continue simplifying, and we get negative p squared plus 2p plus 4, everything over p squared plus 4 squared. Combining like terms, and then 2p and then 4. Of course, I will factor out negative 1. And then I get p squared minus 2p minus 4 divided by p squared plus 4 squared. Always try to simplify the expression, whatever you get. And if there is a negative leading coefficient, take it out. Okay, so now we are asked to find, so we determine the derivative. So there are two possibilities. One, when this function is 0, and the other one when this function is undefined. Let's start with when this function is undefined. Where is this function undefined?
When the bottom is 0.
Good, which means exactly where? Nowhere. P squared plus 4 is never 0 no matter what. So f prime of p, h prime of p is defined everywhere. So no critical number can come from f prime being undefined, h prime of p being undefined. Okay, so now there is one more option. What is that option? H prime of p to be 0. Very good. So that means which portion of this function is 0 if the entire function is 0? The top. P squared minus 2p minus 4 equals 0. Quadratic formula. Negative b plus or minus b squared minus 4ac over 2a. Simplify as much as you can. So then p equals 2 plus or minus is the square root of 20, which is 2 the square root of 5 divided by 2. Finally, 1 plus or minus the square root of 5. These are the critical numbers of this function. Yes, Braden, go ahead.
I don't understand the
Yes?
two conditions for like where a critical number exists.
So critical numbers exist only when the derivative is 0 or undefined.
Because we said h prime of p is defined everywhere.
Yes, it's never undefined. It's a fraction that will never have 0 in the denominator. If it never has 0 in the denominator, it will be defined everywhere.
And then you have to set h prime of p equal to 0.
Because there are two possibilities. One, when h prime of p is 0, none, undefined, no points. And then I have to solve the equation f prime of p equals 0. If I don't get anything, I'll say the function has no critical numbers.
Okay.
But I did get something. I did get two values, and they are critical numbers of the function.
Okay.
Now, if you're asking me, are these going to be max min? I don't know yet. I have not investigated that. But if a function does not have critical numbers, it's guaranteed not to have max min. Only critical numbers can turn into max or min. Okay. One very important topic here is the study of a function on a closed interval. Basically, we're interested in max min, but let me go back to one graph so we can discuss this first. So let's suppose this function, I have a graph of a function that does this. Obviously, there is a minimum here, right? That's a minimum. It represents, in this case, two different types. One which is local, or also called relative. Local or relative. Because I can show an open interval around it where all function values are bigger. It is also an absolute or global. We use those two interchangeably. When we talk about local, we mean relative or relative local, the same thing. Absolute global is the same thing. So why is this local? Because I can show the open interval. Why is it absolute or global? Because there is no other smaller than it. That's it. That's the minimum for the entire function. Now, any questions? Yes, Braden, go ahead. Yes, please.
Can you go back to when you're doing the quadratic formula?
Yes. So it's negative b plus or minus the square root of b squared minus 4ac. And 4 plus 16 is 20, and I simplified it as 2 to the square root of 5. Is that okay? Everyone? Any questions? Is this okay? So
you just pulled out a 2.
you mean from here?
Yeah.
Yes, I factored out and simplified it, or I separated it. 2 over 2 is 1. 2 to the square root of 5 over 2 is the square root of 5. So you either write 2 parentheses 1 plus or minus the square root of 5 over 2 and you simplify factors, or you separate the fraction and you simplify each fraction by itself. So this is a local minimum because I can show the open interval, local or relative, but it's also absolute because it's the smallest possible for the entire function. Now this point here, yes, Jared, go ahead. Nate, go ahead. Any questions?
No, we're good.
Anything? Okay, this point up here, see, I cannot show the open interval because it's an end point. Therefore, this could never be a local. In this case, it's an absolute. But which type? Max. So this particular one, because it's at the end point of the interval, it could never be local or relative. But since it's the largest possible value, y value for this function, it's considered the absolute max. What about this point? What will this represent? It cannot represent a local. It cannot, because it's at the end point of the interval. It cannot represent a local if it's at the end point of the interval. You cannot show the open interval both sides. It's not an absolute because there is one smaller than it. It's not an absolute max because there is many, we have many more above it. So this point is nothing. It's nothing when it comes to max min. Very good. So let's look at problem 53.
Is that an absolute minimum in the example?
Yes, this is a minimum that is also local and at the same time absolute, both.
What does it mean to be local, close to the graph?
Because I can show the open interval both sides, and all the function values are bigger than this one. This function value here is bigger than this. This function value here is bigger than this. This is absolute the minimum. There is nothing smaller than it as a function value.
Okay.
That's the absolute smallest function value for this function.
So because you can show like the interval on both sides.
Then it's a local or relative. But if it's the smallest, it's an absolute or global. But this one is both. It's local and absolute. Does it make sense?
Yes.
Perfect. Other questions here? Okay. So we're looking at 53 on page 281. To illustrate how to study a function on a closed interval. Not on the entire domain, just on a closed interval. Okay, 53. X plus 1 over x, so this is f of x, x plus 1 over x. And we are given the interval, which is, they say 0.2 to 4. I'm going to start with that. We will be in all our tables, if you prefer mine. If you have another one, please use your own. But in all the tables that I will present, the variable is at the top. The first derivative is the first row. And the function, it will be in the middle between the first derivative and the second derivative. You'll see in a minute, later on, we're going to add the second derivative to this. In this case, the domain is forced upon us. I have no say in it. Therefore, I have to write between 0.2 and 4. And I have to study this function between those two. So our first step, we are asked, one more time, let's read. Find the absolute max and absolute min values of f on the given interval. I always like to add local as well. So our first step would be, what do you think? We're looking for max min. Yes, we have to find the derivative. And then after I find the derivative, I will have to find what?
Critical.
Excellent. That's it. So let's find the derivative first, and then critical numbers. Can anyone give us the derivative of this function?
1 minus 1 over x squared.
Excellent. Thank you very much. Great job. So this is actually x squared minus 1 divided by x squared. I have to add or subtract, in this case, the two fractions. I have to change 1 into x squared over x squared, and I get this. Good. We know that critical numbers come from two possible sources. A function doesn't have to have critical numbers. Not coming from both and not even from one or the other. But f prime is undefined, where the function is. But just keep in mind, we are forced to study the function only between 0.2 and 4. So is this function undefined between 0.2 and 4? No, not. Good. So the second possibility is f prime of x being 0. When is a fraction 0? So x squared minus 1 equals 0, and we know this is x equals plus or minus 1. You either factor or you move 1 and take the square root and so on and so forth. I have to go back to the table. Again, I am forced to study this function only between 0.2 and 4. One of these two has no place here. Which one? The negative 1. Correct. So I only put 1 and 0 underneath. Why 0? Because the derivative is 0 when x equals 1. At this point, I will plug in the function, these, and get a number. So let's go to y equals, and punch in x plus 1 over x. Let me change this again. No, not this. This. Okay. Second in table. Oh, I didn't put the function in. So x plus 1 divided by x. And we go to second in table, and I punch in 0.2. I punch in 1, which is very clear, and 4. So I'm going to put these numbers in the table. 5.2, 2, and 4.25. The next step, without looking at these numbers, I will study the sign of the first derivative. So let's take a look at the first derivative. So it is 0 at 1. So let's see on this side with 0.2. The denominator will have what sign? No matter what? Positive. So if I plug in 0.2 in here, just tell me the sign of the top. Do you all agree with negative? What if we plug in 4 to see the other side? What will we get at the top? Good, excellent. We established something last time in which we said, if the derivative is negative, the function must be doing something, decreasing. If the derivative is positive, the function must be increasing. Okay, so now let's see if the two rows work well together. From 5.2 to 2, what does the function do? Is that supported by the sign of the first derivative? Correct. From 2 to 4.25, what does the function do? Is that supported by the sign of the first derivative? So now I can conclude that these two work well together. Obviously, I'm expecting that there is no error anywhere. Okay, now we have to establish what 0.2 comma 5.2 means, 1 comma 2, and 4 comma 4.25. We have to establish and write what those mean. Since 1 comma 2, the function decreases towards it and then increases. What can I say about 1 comma 2? It's decreasing, 0, and then increasing. It's definitely local min. Now the question is it an absolute min? It's also an absolute min. There is no other smaller value than it. So I will write for 1 comma 2, local, and absolute min. Excellent. Now let's go back and see what we can write about 0.2 comma 5.2 and what we write about 4 comma 4.25. What do we write about 0.2 comma 5.2? It cannot be local because it's at the end point of the interval. Never local at 0.2 or 4. Not possible because I cannot show the open interval. Is it an absolute max? Okay, I agree. 0.2 comma 5.2, it's an absolute max. Yes, Braden, go ahead.
Why is it a max when it's decreasing?
Because it has to be decreasing from somewhere. It's decreasing from 5.2 to 2 and then increasing to 4.
Okay.
You see that? 5.2 for the y value, decreasing to 2 and increasing to 4. Better? Perfect. What can we say about 4 comma 4.25? Nothing. Nothing when it comes to max min. Okay. Any questions on this? Any questions? Yes, please, Savannah.
Do we have to check the other numbers outside of the interval to tell if it's an absolute?
Excellent question. We are forced to study the function on this interval. We don't care about anything else.
All right.
Very good question. So this was how to study a function when it comes to max min. So the whole topic in this section is max min. We're talking about max min in 4.1. So this is a special case in which we have a function that is given to us on a closed interval. And this is how we study what the function is doing on a closed interval when it comes to max min. So we determine the derivative. We determine the critical number or critical numbers. We study the sign of the derivative. We determine the function values at those points. And then we analyze what happens. Always make sure that, for example, if I have here 1 and here I have 2, and this shows decreasing, from 1 to 2 is increasing, then I know I have a mistake somewhere. There's a discrepancy. So from 5.2 down to 2, that is correct. It's supported by the sign of the derivative. From 2 to 4, yes, it's increasing, and it's supported by the sign of the derivative. So always remember these two rows have to work well together. Any questions? Yes, Regan?
When you're doing the intervals from 0.2 to 5.2 and 1 to 2, how do you know that it's an absolute max and a local or an absolute min?
These?
Yeah.
A very good question. These are not intervals. This is the x value and this is the y value. This is a point. I know it's confusing. You're right. I should have said that. So this is a point. 0.2, 5.2. 1, 2, and 4, 4.25. These come from the table. The x value, the y value. The x value, the y value. The x value, the y value. Is that better?
Yeah, I just don't know how you can tell from that one of them's an absolute max and one of them's a local and absolute min.
Very good. So follow my hand. This is 5.2. The function is decreasing to a height of 2. Now the function is increasing to a height of 4. You see the 5.2? It's a function value. 5.2. It's decreasing to 2. This must be the minimum because right now it starts increasing to 4.
So wouldn't that not be absolute?
That is absolute as well. It's local, but also absolute. Does it make sense?
No.
So what if I do this? I will plot 0.2, 5.2. 1, 2, 3, 4, 5. This is 0.2, 5.2. You agree with this point? Okay, then 1, 2. We agree with this point? And then I have 3, 4, and 1, 2, 3, 4. Okay. So the graph, I'm not graphing the function. I'm just giving an idea. Is it clear why this point is an absolute max?
No. I understand why it's a max, but I cannot tell the interval on the other side, so it's not absolute.
But we are given this. We cannot go outside of this.
Okay.
We don't care what the function does anywhere else but here. We are only studying the function between 0.2 and 4. That's why I put 0.2 at the beginning and 4 at the end. Nothing to the sides. There is no 0 here. There is no infinity. There is no negative infinity. That's all we have. So from 5.2, it drops to 2 and goes back up to 4 point something. Is that clear why it's an absolute max?
Yes.
Is that clear why 1, 2 is an absolute min, and I can show the open interval for the relative as well?
Is the max local as well?
There is no local at the endpoints. I cannot show the open interval. No local or relative at the endpoints. So this is only an absolute max. But this one is in the middle of the interval. It's an absolute min. There is nothing smaller than it. But it's also local because I can show the open interval. The function exists on both sides.
Okay.
This one doesn't mean anything because it's not the maximum, it's not the minimum, and it cannot be considered a local. Is this better?
Yes.
Perfect. Any questions? Any questions? Okay. Thank you for asking because I'm sure other students may have the same idea. Okay, so we're moving forward. 4.2, 4.2. Yes, the Rolle Theorem, R-O-L-L-E, Rawls Theorem, and the mean value theorem. Two theorems. We are not going to do a lot with them, but they are important, so I'm going to show you a couple of examples. So let's start with Rawls Theorem. Let's look at the graph. That that starts at this point of a function between a and b. This is point A, this is point B. This is our function f of x. And can anyone tell us what is this?
F of x.
Yes, f of A, which is also f of B. So this is, you would say, it's a very specific case, and I would have to agree. A function starts at this point, a comma f of A, and somehow it comes back to the same point. There are three hypotheses of Rawls theorem. Number one, f continuous on a comma b, and you tell me if you agree. Is a indeed f of x indeed continuous on a comma b?
Yes.
Perfect. Number two, or part B, or two, f differentiable on a comma b. I'm not saying it's not differentiable in a or b. I'm saying it doesn't have to be differentiable in a or b, so I did not use a closed interval. And condition number three, which is very clear, f of a and f of b are, yes. Okay, I'm going to start the conclusion, and you're going to help me finish it, because I know you can. If all these three conditions are fulfilled, then by Rawls theorem, there exists a C in the open interval a comma b such that
F of c equals 0.
f prime, very good, awesome, f prime of c is 0. It must have a term, at least a term. So right here is C, where the derivative is 0. So how can a function be continuous and differentiable, start at this point and come back to the same height if it doesn't have at least a term? Can it have more than one term? Yes, it can do this. It can have as many terms as you want, but guaranteed at least one. I'm sorry, I forgot to turn off my phone. Okay, disregard it. Sorry about that. Good. So let's look at it. Yes, let's look at an example. On page 288, problem 2 on 288, we are given function f of x, which is x cubed minus x squared minus 6x plus 2, and we are given the interval 0, 3. Let's read the question. Verify that the function satisfies the three hypotheses of Rawls theorem on the given interval. Then find all numbers C that satisfy the conclusion of Rawls theorem. Okay. I cannot draw any conclusion before I state whether the function is continuous on 0, 3 and y, whether the function is differentiable on 0, 3 open and y. After I verify that f of 0 equals f of 3, and only then I can draw the conclusion and also find those numbers. So number one, is f of x continuous on 0, 3? Excellent. Why? It's a polynomial, it's continuous everywhere. So I have to write f of x continuous on 0, 3 as a polynomial function. Excellent. Two, f of x differentiable on 0, 3 at least. Why? Not because it's continuous, because we know that functions that are continuous not necessarily are differentiable, but for the same reason. It's a polynomial function. There are no restrictions with polynomials. as a Pauli function. Now condition number 3. If condition number 3 is not fulfilled, I will say, sorry, I cannot apply Rawls theorem. So now I have to find f of 0, and I have to find f of 3. If they're not the same, I'll say, sorry, Rawls theorem is not applicable here. How much is f of 0? 2, very good. How much is f of 3? 27 minus 9 minus 18 plus 2. So, very good. So, are all 3 conditions fulfilled? Good. So now I have to say, by Rawls theorem, there exists a C in the open interval 0, 3, at least one C, guaranteed, such that, what do I have to write? Of course, it must be a term somewhere, a max or a min, at least one. So let's find f prime of x first. Can anyone give us f prime of x?
3x squared.
Yes?
Minus 2x.
Yes?
Minus 6.
Excellent. So I will write 3c squared minus 2c minus 6 equals 0. You don't have to change this into c. You can just solve the equation and then come back and say this is c. That's fine too. So let's solve this equation. C equals negative b plus or minus b squared minus 4ac. 4 times 3 times 6 divided by 6. So this is 2 plus 2 to the square root of 19 divided by 6. What I did was I took 4 outside. I pulled out a 4. The square root of 4 is 2. And then 1 plus 18 would be 19. I will simplify, and I get 1 plus or minus the square root of 19 over 3. I have to approximate these two numbers. Why? Yes, I'm sorry, Ricky. Better? Why do I have to approximate these two? Because the interval is 0, 3. So I already know that one of them will not fit. Which one? The one minus the square root of 19. It's not going to fit. It will be outside of the interval. But I still have to check that 1 plus the square root of 19 over 3 is between 0 and 3. We should. It is. But that's very good. Okay, so 1 plus. Don't forget parentheses. 1 plus the square root of 19. Divided by 3. Yes, 1.78629. I'm not going to write this. I just need to verify. Yes, that's correct. So I would say only 1 plus the square root of 19 divided by 3. The other one will be a negative number, which will not fit in 0, 3. In the interval 0, 3. Any questions? Any questions on Rawls theorem? Please, Vanessa.
So it was easy to find it because it was a polynomial. What would be an instance, or like, do you have like an example if it wasn't a polynomial?
Yes. Yes. We can look at any example. The only thing is that we have to say that it's differentiable, show that it's continuous and differentiable, and then find that the third condition. Yes. Let's take a look at, I see number 3. Number 3 is not a polynomial. Very good question. 3 on the same page, 288. So we have f of x equals the square root of x minus 1/3 x, and we are given 0, 9. Perfect. So the same question here. We are given this function, and we are asked, verify the 3 hypotheses. If all are valid and correct, for this function, then find C guaranteed by Rawls theorem. So, number one, f is continuous on 0, 9 as a difference of two continuous functions. This one is a polynomial, and this one is the square root, which will always be continuous on 0, 9. And we know the graph. Number two, f is differentiable on 0, 9 for the same reason. You can copy it again if you want. Because it's a difference of two because it's a difference of two differentiable functions. Let me write it better. As a difference of two differentiable functions on 0, 9. Now, I have to test the third condition. What am I testing now? I'm testing that f of 0 and f of 9 are the same. If they're not, then I'll say, sorry, Rawls theorem doesn't work here. How much is f of 0?
0.
Perfect. How much is f of 9? How much is the square root of 9?
0.
The square root of 9 is 3. Yes, and 9 over 3 is 3. 3 minus 3, you're right, it's 0. Since all three conditions are fulfilled, what do I conclude? How do I write a conclusion? Therefore,
By Rawls theorem,
yes,
there exists
by Rawls theorem, there exists a C in the open interval 0, 9, such that
f prime of c equals 0.
f prime of C equals 0. Now let's find f prime of x first. Can anyone give us f prime of x?
1 over 2x
Excellent. Minus
minus
1/3. Very good. Great job. So now we want f prime of c, 1 over 2 the square root of c minus 1/3 equals 0. And we are solving this equation for, obviously, for c. Good. So let's move 1/3 to the other side. So this is a simple type of equation. Here's one. First of all, it's a proportion. Those two fractions are the same, have to be equal, and they have the same numerator. What has to happen for the two fractions to be the same if they're equal and they have the same numerator? They must have the same. That's it. They must have the same denominator, or you just cross multiply. 2 the square root of c equals 3. How do we solve this equation, and what type is it? It's a radical equation. Very good. Radical. Yes. Excellent. Thank you so much, Regan. Very good. Well done. So this is 4c equals 9. So c equals 9/4. This better be between 0 and 9. I don't. For this one, I don't have to check. It's definitely between 0 and 9. Is this better, Vanessa? Perfect. Any questions? Ricky, go ahead. Anyone? Any questions on Rawls theorem? Yes, Brayden?
I don't really understand what it's saying. Is it just saying that the 2 points in the open interval give 0 equal if the conditions are met?
No. Here's what it says. It's as more of a common sense. It's not a brilliant theorem. It's really brilliant because it was created many, many years ago. But it only says this. If a function is continuous and differentiable, and at some point in time it's the same value for any pick two x values, it's the same height, then there must be a term somewhere.
Okay.
Right? At least one. If it's continuous and differentiable. If it's not continuous and differentiable, I can guarantee that. But if it's continuous and differentiable and on the graph anywhere at two different x values and it has the same height, you must turn somewhere. You must have a turn. You must have a point where the derivative is 0. at least one, right? Because the function basically can do this. How many terms does it have? 1, 2, 3, 4, 5. It has 5 different points C in this interval where f prime of C is 0. But the theorem says if it's somewhere here the same height, it has to turn at least once if it's continuous and differential. Now, the next theorem is the mean value theorem is more sophisticated. Let's talk about that. The mean value theorem. The mean value theorem is more relaxed, does not require the third condition of Rawls theorem, just the first 2. So let's look at a situation. Now, what is the practical application, right? Because I'm sure that's what you had in mind. Okay, so you're telling us that the function must turn somewhere, blah, blah, blah. So what? So what's the practical application? Practical applications are in solving inequalities, showing that polynomials have such and such terms, in solving different types of equations, finding how many solutions, real solutions, the equations have. So we're not going to go into that extent, but we need to talk about these 2 theorems. Okay, so here's another situation. Point A, point B. This is not the function. This is not the function. This is just a line segment between A and B. And I'm going to say this is the function. So this is the function f of x. Yes, we talked again about interval a comma b. Moving forward, please get used to it. I'm going to talk about at least in this chapter several times and in chapter 5. A comma b, a comma b. Good. So I will copy from Rawls theorem. Obviously, you will probably agree with me that f of x is continuous on the interval a comma b. And number 2, f of x differentiable on a comma b. Do we agree with that? There are no other conditions here, just these 2. And now watch what I'm doing with this function. So this is a line segment. It's a secant line, right, between crossing the function in 2 points, in point A and point B. So here's what I would like to do next. I draw parallel lines to a comma b till this point where I draw the tangent line to the graph of f of x, and it happens to be this point. Now, I hope you agree that the slope of this line, I'm going to call it m1, and the slope of this line, I'm going to call it m2. The way I drew the picture, obviously, m1 and m2 are the same, of course, because I drew parallel lines, right? And we know that parallel lines have the same slope. Agreed with that? Yes? Good. So now, I would like you to determine for me m1. I'm going to say that this is c. So I want the slope m1, and then I want the slope m2. And we know that m1 equals m2. So I would like the slope of m1 not connected to AB. And then I want the slope for m2, the slope of the second line, or AB, of course, not connected to m1. So what will you say about the slope of the tangent line m1? Excellent. Great job. Thank you, Chris. Okay, now I need the slope of the line m2. What will you say? So maybe I should give you a little bit more information. I know you have it, but maybe it's better to write it. What is this?
F of C.
This is f of A, and this is f of B. Good. Ready. When you are. Yes? F of B
B minus A.
Excellent. But we know that these two are equal. So f of b minus f of a divided by b minus a is f prime of c. This c in the interval a comma b is guaranteed by the intermediate value theorem. In short, MVT. Not the intermediate, I'm sorry, mean. Intermediate value theorem is something else that we already discussed a long time ago. So, mean value theorem. So, because these two conditions are fulfilled, there exists, so by MVT, there exists a C in the open interval a comma b such that f prime of c equals f of b minus f of a over b minus a. Slightly more sophisticated, not simply a term, but this says something else. It says that between any 2 points, if you want to find the rate of change, it's equal to the rate of change at a particular point. One more time. If you want to find the rate of change between A, B, you can also find it with f prime of c. That's all it says. Yes, Savannah?
More than one C?
Yes. At least one. Very good. So now let's talk about, here it is. Verify that the function satisfies the hypothesis of the mean value theorem on the given interval, then find all numbers C that satisfy the conclusion of the mean value theorem. Okay, let's look at the natural log because we haven't looked at the natural log before. So natural log is number 11 on page 289. We have f of x, which is natural log x. The interval is given to us 1, 4. So we're asked to verify the hypothesis of the mean value theorem. How many hypotheses? Rawls theorem has 3. Mean value theorem has only 2. Does not restrict with a third one. We know the graph of this function. We graphed it many times before. What can I say about f of x? Is it continuous on 1, 4? Very good. Continuous on 1, 4 as a log function. Continuous on its domain. Number 2, is f of x differentiable on at least the open interval 1, 4? Yes, there are no corners, no cusps. Yes, that is correct. As a log function. Because both our conditions are fulfilled, we will say by MVT there exists a C in the open interval 1, 4 such that f prime of c equals f of 4 minus f of 1 over 4 minus 1. Indeed. Let's find the